So again, showing equation m d2 delta dt2 is equal to pm minus pe. So from the previous slide, I am just substituting value of pe. So pe is equal to pe naught minus del pe del delta at delta equal to delta of minus, sorry, it is in into del delta. I am just substituting this value at the place of e. Next, at initial or before disturbance at initial, we have already seen that Pm is equal to Pe naught. So d2 delta dt2 is equal to these two are cancel out. Pm and Pe naught cancel out. So only del Pe del delta into del delta terms is there. So again we can write, or we know, delta, this rotor angle is equal to initial rotor angle plus change in rotor angle, that is constant. So del delta del t is equal to del t in terms of del delta. Again, del 2 delta del 2 t will be getting del 2 del tt2 del delta. So again, at the place of delta 2 delta 2 t, we can substitute these values. So em delta 2 del delta del t2 plus del pe del delta at delta is equal to delta naught into del delta. So finally this is coming m into delta 2 d delta t2 del delta plus del pe del delta du into del delta is equal to 0. Just doing this way. That is for delta is equal to greater now. Already I have written this one in previous slide. So here I am taking m into plus k into del delta. K is one constant. K is equal to this value. Del E del delta that delta equal to delta. So again we write m del delta. No, okay, I am doing this one dividing both side by m. So it is coming plus plus k by m del delta is equal to 0. So I am taking del delta common. So it is coming delta 2 plus k by m is equal to 0. So as here I am taking d is equal to del t. So again here we can write del t d square plus k by m equal to 0. So for second order differential equations, that means roots of equation, we can write d is equal to plus minus root under minus k by m. So case 1 from this equation, case 1, if k less than 0, then d has two equal roots. Two equal roots. So that is equal to plus minus root under k by m. So from this equation we will be getting del delta is equal to uh, del delta is equal to, we will be getting c1 e to the power k by m into t plus c2 into e to the power e by m into t. So for k less than or equal to 0, it is unstable. Similarly, for k greater than 0, roots are complex. Roots is equal to complex. So it is stable. So for the stability criteria, we can write del EE by del delta less than or equal to 0, that is unstable. That means delta belongs to 90 degree to 180 degree. That means P max cos delta less than 0, and when del PE del delta greater than 0, that is stable. That is delta belongs to 0 to 90 degree. That means P max cos delta greater than 0. Another one is del PE del delta is equal to 0. Marginal stable. Marginal stable. That means delta is equal to 90 degree. P max cos delta is equal to 0. It means maximum steady state stability limit is P max. So if we plot the curve P and delta, so this curve will look like this. So up to this, that is 90 degree, and that is P max. Above 90 degree system is unstable. So if any time power requirement is greater, then system will be unstable. That means we can say if the power requirement is greater than the uh, maximum power generation, then system will be unstable. Next, methods to improve steady state stability limit. Methods to improve steady state. Number one, we know P is equal to EV by X, that is P max. So if V is constant, terminal voltage is also constant. So excitation increased. If excitation increased, so that is overexcited. Again, if X is reactance is decreased, or it means reducing the inductance, we can improve the steady state stability. And inductance can be decreased by using bundling of conductor, double circuit line, and series compensation. Series compensations. And by using SBC, static bar compensator, we can also improve the steady state stability, by injecting reactive power. Next,